Hi and welcome everybody to the second part related to OTFS waveform, a 2D modulation waveform scheme. Now in this part, this is the second part. In this part, we will compare it with OFDM mathematically. We will understand the mathematical notation of these waveforms in 2D and also understand the general structure in delayed Doppler domain and its transform in time frequency domain and its different implementations. So as we know, let's just give a brief overview about OFDM, the key assumption that was used in OFDM to develop it. OFDM, the development of OFDM modulation typically assumes this assumption. They assumes a slowly varying channel with impulse response h tau t equal h of tau. Please mute your mic from your side. Everybody, there is noise. There is noise. Thank you. So now it's clear and hearable. Everybody can hear what we are talking about. So I'm saying the key assumption for OFDM was assuming a slowly varying channel with impulse response h tau t equal h of tau. That's locally independent of the time variable t. With the addition of a cyclic prefix to the data to ensure the channel effect is a circular convolution, we obtain a multiplicative channel model in the frequency domain. Yes, this is what we were simulating last week in the OFDM tutorial. You have your data modulated symbols in the frequency domain, and you have the channel in the frequency domain, the noise, and you have your received vector. This is defined for the frequency bands that we can see here from minus m/2 till m/2 minus 1, where hm is the frequency response of the channel evaluated at multiples of the subcarrier spacing. The channel frequency response is given by this formula given here. hm is equal to the Fourier transform of you basically take your channel from time domain to frequency domain. This is the mathematical formula to do that. We did it last week in MATLAB environment where we took the FFT. Now, to develop a modulation scheme suited for the time frequency fading channel, we need to avoid the time invariance simplification and examine the full effects of the time varying channel on the transmitted waveform. Therefore, we will not use h tau t, the one we mentioned in the first part of this lecture, which is the time varying impulse response characteristics of the channel. Because it's less useful, as it doesn't tell us exactly what the channel is, how many reflectors are in the channel, what's the distance of these reflectors, and what are the speeds of these reflectors. We don't have any idea when we use time varying impulse response. Instead, we will use delayed Doppler response, and which can give us more information. So basically, the channel operation on the transmitted waveform under the delayed Doppler the delayed Doppler response can be represented in equation 3, where you have st minus tau is your waveform, and this is your received signal, and this is the channel operated on your waveform. The delayed Doppler impulse response has an appealing physical interpretation. For every point Tv, the value of the channel represents the reflectivity of a cluster of reflectors sharing these specific delay and Doppler parameters value. This is the beauty of this waveform. That's why it's more useful than the time varying impulse response. The parameterization, however, the parameterization tau v and h tau t are equivalent. They are exactly representing the same thing. But one of them is mathematically friendly and physically meaningful, and the other is not. Both of them can be described in general time varying systems. Both of them describe general time varying systems. In fact, the two parameterization are related by an appropriate Fourier transform along the t-axis. This is the thing you need to know about this about this definition of the channel. The main thing to notice is that T delayed Doppler channel representation is much more compact and physically meaningful and mathematically friendly. This fact can be exploited for the purpose of channel estimation and equalization, because in this case you need to estimate less number of parameters, and due to this you spend less resources to estimate your channel and get the data. Using the channel equation in 3, we can derive a channel model in the time frequency domain for the given bandwidth and TTI domain, travel time during interval. This TTI stands for travel time interval of an OFDM system. So for OTFS, the equation that you saw here for OFDM 1D becomes this equation 2D, where you have the time and the frequency simultaneously, which are the transform of delay Doppler. So M stands for frequency bins and N for OFDM symbols. Now this is the channel in delay Doppler domain. Basically, each tuck here, each column represents specific the reflection from specific object with certain distance and certain Doppler, certain speed. And this, as you can see, this is tab 1, tab 2, tab 3, 4, 5. We have 7 tabs, and we have different Dopplers. At each tab, we are receiving the same signal at different frequencies. Now, when you take the two-dimensional Fourier transform, this you got image processing, yes? Think of it like FFT2. This in MATLAB, it's kind of FFT2, not FFT alone. Two-dimensional. When you take the two-dimensional Fourier transform of this, you get the channel time frequency response, which looks like this. So as you can see here, it's sparse. There is spacing, zeros between the tabs, not compact. And here it's like, as you can see, it's continuous and more smooth, and has values over all the values of time and the frequency. Okay. Equation 5 can be thought of as a 2D Fourier transform version of the delayed Doppler impulse response. This figure actually very important that you can see this in MATLAB. Make sure now, after you finish this lecture, you go home and you generate this channel and see this channel in delayed Doppler domain. If you can get this, then your hands are full on the problem, and you know how to handle it in MATLAB and how to generate it and see these figures. And the MATLAB previous tutorial is a big help for you. Plus, you need just to add a new dimension and use FFT2 instead of FFT1. And here the channel here, you define it 2D. It's like a matrix, not vector, because you have values not only in one row or one column. You have multiple rows, multiple columns. This is how you define it in MATLAB. And you take FFT2 of this, you can draw this. This you can draw it plot 3 function, plot 3 or surface 3, okay? And this is the mathematical formula. HNM is basically this. Yes, HNM. This is it. It's basically this one. And H tau V is this one. And this is the transform, the FFT2 kind of. Not really, but kind of, think of it. Symplectic Fourier transform this, because one is minus and the other is plus. Good. I believe some of you got the idea of how to obtain this in MATLAB. Equation 5 here can be thought of as a 2D Fourier transform version of the delayed Doppler impulse response. It's called the symplectic Fourier transform. In MATLAB, think of it FFT2 function. Based on the channel equation 4 and 5, we wish to derive a pre-processing step now. Now we understood the channel, we understand how the channel in delay Doppler, how the channel in time frequency domain. Now we will derive a pre-processing step that can eliminate the effect of the channel on that can compensate the effect of the channel on the data that we transmit, and make sure that it's independent of the duration of the TTI. To this end, we basically, in this modulation scheme, we map the information bearing QAM, the QAM symbols. You put them instead in the OFDM example that I explained in the OFDM tutorial for the MATLAB simulation. In this case, what do you do? You put your symbols in matrix, not vector. Here, your QAM symbol, the complex. You put them here, here, all of them. Yes, until you fill the matrix. And we call this XL, this dimension. You transfer it to NM time frequency via a 2D complex exponential basis function. What's this exponential basis function? This is not the column of the IFFT only. This is another column in another dimension that takes FFT. FFT with IFFT in 2 dimensions. This is it. E to minus j2 pi and 2 independent variables, time and frequency, not 1 variable. And this is here. It's this one. And those are your QAM symbols here. You get them, you define them from the QAM modulation. And this, the summation for all, to take all the columns and rows. And divide over Mn for normalization to make sure that all the vectors are unity. So what's the difference from OFDM? Can you tell me? It's easy, it's 2-dimension waveform. It's a 2-dimensional waveform that has basis function of 2 dimensions. That includes FFT and IFFT simultaneously. And your symbol, each symbol in this domain, will be mapped and carried by 1 exponential basis function. And then you sum all these exponential basis functions together. Clear? Let me now give you a picture to make it even much clearer for you. Here is the matrix that I was telling you about. Okay? And this is the first QAM symbol. You multiply it by the first 2D carrier, basically, and the second by the second exponential carrier. And this is the third, this is the fourth. And then you sum them. Basically, this is the equation. This is the equation here. Looking more carefully at the basis function, PKL, NM, KL is delay Doppler, NM is time frequency. We have the following remarks. Along the frequency band dimension M, the basis function, this constitute a set of DFT basis function and relate the frequency domain to a new domain. We call it delay. So the delay in the delay Doppler domain is related to the frequency. In the second point, it says that the time is related to Doppler. Constitute a set of IDFT basis function and relate the time domain to a new domain. We call it the Doppler domain. This is for N. In conclusion, the OTFS scheme allocates the information QAM symbol that are located in the delay Doppler to time frequency domain via mapping process. The mapping of information symbols to time frequency basis functions is illustrated in the following figure. This figure here. So do you see with me that it's very similar to OFDM? If I ask you what are the key differences in terms of math between OFDM and OTFS, what do you tell me? I have one summation here. In OFDM, I have one summation. Here I have 2 summations. In OFDM, I have only the symbols are defined in 1 dimension. I have them in 2 dimensions. In OFDM, I have only one dimensional basis function. Here I have 2-dimensional basis function. The result here is matrix or 2-dimensional array. There the result is vector again. That's mathematically the difference. But physically the difference is huge. And the implication of that. So we talked about And at the receiver side, what do you do? What do you do? I will ask you before I tell you what we need to do. What do we do at the receiver side? You just, these are the basis function, you multiply by their conjugate. So if you take, if the first is FFT and the second IFFT or DFT, IDFT, you just make the opposite by just multiplying with the conjugate. You take Y, this is Y. X, after you transmit it over the channel, this is X. After you transmit it over the channel, you get Y. Y, you multiply it, the received signal, you multiply it by the complex conjugate of the two-dimensional basis function to get X hat LK. And the complex conjugate, as you can see, the first now is plus and the second is minus. Okay? Now, let's go to the implementation. OTFS demodulation structure. How do you do that? With coding. First, you have your data bits. Then you perform forward error correction coding, which is basically increase the length of your data bits or add redundant bit to protect you from the channel impairments. And then you have symbol mapper here. Yes. And after that, yes, the symbol mapper here is basically QAM. Think of it like a QAM modulation, but map the bits to symbols, complex symbols. And you form a matrix of these symbols. CX is a matrix, multiple rows, each row multiple elements. And then you take IFFT along IFFT along each axis, along each column here. You take the IFFT of this along V, yes. You end up getting this row, this first row. The second one, you take this row. Third one, you take this row. Third, four, until you finish them. And then you interleave them. You put them adjacent to each other. This is the first. Then you put this adjacent to it. You put this adjacent. And you send them all together. And you convolve this transmitted the whole transmitted packet with the channel response over TTI. Travel time interval. I mean, you capture the full characteristics of the channel, and then you receive it. You wait until you gather all these symbols and put them one on top of the other, one on top of the other, and form what? Form a matrix like this. And then you take FFT along time to get another matrix X, which represents the complex symbol, and then you decode them, and then get the bits that represent your transmitted message or whatever. This is ZAC transform implementation, but there is another implementation that takes the 2D altogether. So let's go to the second implementation, and basically you can implement this in MATLAB. It's similar to OFDM. You can try it in MATLAB. It can be maybe a question. Just implement this in MATLAB and get reliable bit error rate. Straightforward. The ones who followed OFDM simulation tutorial, now they can do magic. They are unstoppable. They learned the OFDM, every single line in OFDM. They are even building new functions and the new methods based on the OFDM subcarrier power modulation and other. So now whatever new example or whatever new modulation scheme, they can quickly simulate and get and debug and know the errors and get the bit error rate and the spectral efficiency. So things like this are expected from you to be learned so that you are expert in simulation, expert in implementation. You know how to put things together, convert them from words, from math into codes, and then push them to the hardware and transmit your OTFS signal over the air. So it's not difficult. You just now move from theory to practice. The second implementation, we use pre-processing and post-processing processes. This implementation coexists with OFDM modulator. Why is that? because the standard, the 5G standard, decided to use OFDM, so they wanted to coexist OTFS with OFDM to make sure that we can get the benefits of OTFS as well. But the problem here, you increase the complexity of your transmitter and receiver unnecessarily. I could have eliminated OFDM, but OFDM in the standard, so I add OTFS as an additional overhead block to get some of the advantages of OTFS. But whether these advantages can compensate for the complexity introduced, we don't know whether it's worth it or not. But it's really significantly much more complex by doing so. This block diagram is analogous to the pre- and post-processing of DFT blocks used to implement single carrier FDMA or zero-tail DFT spread OFDM on top of the underlying OFDM. You remember with me OFDM, and I asked you one time the difference between OFDM and single carrier FDMA. I told you we used one DFT before I50, before IDFT, and another IDFT at the receiver after DFT. So basically you have two at the transmitter, two at the receiver. Here kind of similar analogy. You have two processing at the transmitter, two processing at the receiver. But here 2D, the processing blocks here is a 2D operation. 2D operation. Think of it like this is FFT2. Also this, you should be able to implement this. This is not difficult too. It just normal OFDM, you already implemented it, you already have it. Before I50, before the I50 of OFDM, you can do perform this processing, and after the FFT you perform this processing to get the advantages. In this case, your signal will be robust against Doppler. How do you know it's robust against Doppler? You need to build a new channel that includes Doppler and see whether you need to estimate Doppler and compensate for it, or automatically your signal is robust to these imperfections. Okay? This is the visualization that shows you what you need to do in MATLAB exactly. You have the delay Doppler domain. Let's start from here. Yes? You have the delay Doppler domain, which is this. You have your equam signal in the delay Doppler, and you have the time frequency domain. You get this after using 2D OTFS transform, which is the symplectic transform or FFT2 transform with certain, you need to be careful about the signs. So this straightforward. You define matrix, contains QAM symbol, and then you have the FT time frequency domain, and then after that, what do you get? After that, you transfer it to time. It becomes multi-carrier filter bank kind of, and you transmit the symbols one by one over the channel. And then you have at the receiver, you take the received symbols one by one, you put them on top of each other until you build a matrix like this, and then you take the inverse Fourier transform to get the symbols in delay Doppler domain, and then you do the equalization here in the delay Doppler domain, or sometimes the equalization can be done after in the time frequency before the delay Doppler, because it's much easier to do it there. And this is the channel. This is the convolution process, multiplication, and this is the physical parameters of the channel that you are transmitting over them. And this is using variables and numbers. For example, I told you you build a matrix, yes? And this along tau, this along V. Tau here, after the transform 2D symplectic Fourier transform, fast Fourier transform, this is, think of it, FFT2. This line here, yes, with me, you are with me here, this line here along N goes to the one along F in the time frequency domain, and this along V goes along N here. So this is the relationship between them. This is the delayed duration, Doppler duration, and here you get 1 over TR determines the spacing between this. Think of it like this is the OFDM symbol duration. 1 over TR determines the subcarrier spacing. And VR here, VR is the length of the channel, TTI. Oh, this over it, you get the duration of one OFDM symbol. Okay, clear? So the bandwidth, if I ask you about the bandwidth is basically M delta F, and the total duration M delta T. Now let's get into the details in the following picture. So you have your QAM symbols. You place them on top of two-dimensional. You intend to place them on top of two-dimensional waveform. This is a QAM 1, QAM 2, QAM. You fill the matrix, whatever. And this is the VB here is the Doppler duration, and TB is the delayed duration, and delta tau here, the spacing, the delay spacing, and delta V, the Doppler period. We call this Doppler period, delay period, and this is the duration of the transmission. So if from the delay period you can get the bandwidth, which is 1 over 100 nanosecond, you get the bandwidth 10 megahertz. From the Doppler period delta V, you get the duration of your transmission, TTI, 1 millisecond, 1 over 1K. And to get the number of symbols you can transmit, yes, in the bandwidth, you basically you have 50 microsecond, the total duration. Over how much? Over the, you can place one QAM symbol each 100 nanosecond. So you divide 50 over 100 nanosecond, you get how many symbols you can transmit along within this duration. And for the other dimension related to Doppler, the duration is around 20 kilohertz, the total bandwidth that you can use for transmission, and the Doppler period is 1 kilohertz. So divide them over each other, you get 20 symbols you can transmit along that direction. As you can see, along delay you can transmit more. So this is how you place the parameters and put them and assign them properly based on the, of course, this information you are getting them from the channel, from the behavior of your system. You need to decide on these values properly, not randomly. Based on, you get them from the channel. They are related to the coherence time, coherence bandwidth, and delay spread, Doppler spread. Okay, from these we are getting these values, and then you can, after the symplectic Fourier transform, this is the matrix you have that contains the QAM. After the symplectic Fourier transform, you have time frequency domain. Yes, basically tau maps to frequency and V maps to time, and you get also new definitions of variables. Now you have delta T, delta F, subcarrier spacing, and this and that. Delay Doppler, we didn't have something called Doppler carrier spacing and this and that. Now you get new parameters, a new definition that can be exactly mapped to the previous calculations, 1-to-1. So no worries about that, because they are basically another view of the parameters here. Now, this is the convolution process that you end up having. The detected symbols are basically the original symbols convolved with the channel with these parameters plus noise. The end-to-end channel in the delay Doppler domain is given by 2D circular convolution. Now we talked about 2D waveform, 2D transform. In time domain, what do we call the in the convolution domain? What do we call this process? 2D circular convolution. In OFDM, we have 1D circular convolution. Here you have 2D. What does this mean for the students who took image processing? 2D image convolution. Have you done that with filtering the image with like another filter that's 2D, X and Y? This is kind of similar to that concept, but now waveform with channel. The waveform is 2D and here you have the channel is 2D. Think of it in image processing. The filter is 2D and the image is 2D and you are filtering them with each other. Similar concept. In image processing we use 2D circular convolution as well. Not linear convolution, 2D linear convolution in image processing. But here linear doesn't fit in our scenario. We have to use circular. This equation indicates that the end-to-end transmission scheme in the delay Doppler domain can be thought of as a 2D convolutive scheme over the whole TTI in both the delay and Doppler dimensions. The delay Doppler impulse response is a continuous 2D circular convolution of the delay Doppler channel response. Yes? It's the circular convolution with a two-dimensional kernel introduced due to the finite transmission bandwidth and TTI or OTFS frame length. This is the delay Doppler is related to the transform function and the channel after the transformation process. 2D circular convolution is a very important concept here. Everything now, in the OFDM we used one guard band, one CB, this. Here you need to think of something in 2D. Everything that was used in 1D, 2D. So visualizing these is not straightforward and implementing them. You need to be really very careful with that and how things should be implemented in order to get accurate answers. So in summary, the summary about OTFS waveform, two-dimensional waveform that uses symplectic Fourier transform and that can map and couple with a two-dimensional delay Doppler channel. In this topic, the delay Doppler domain provides a novel view of the effects of the wireless channel and points to significant benefits when modulating information symbols in that domain. So it's basically gives you deeper understanding and makes the equalization process and detection much easier and based on math and based on systematic analysis. And also you extract the full diversity of the channel basically because you are transmitting your data over the whole TTI of the channel. But what's the cost of this basically, since you keep stacking your packet until they are full matrix and then you transmit it? Delay. It causes lots of delay because the channel TTI might be long. To capture the whole TTI, you need to wait for a long period of time. So this scheme can kind of suitable for high-speed environment where TTI quickly changes and not that big. It's not, TTI is usually short. But for static channel, you don't need OTFS basically. You won't get too much benefit from OTFS in static channel. You know this point? This is very critical point. As we used to do in each presentation, each lecture, we mention the topic, we understand it, and then we start thinking what are the limitations and drawbacks of this. Although they are not written or they are not discussed too much in the literature, but we should think. Yes, we are thinking with each other. What do you think when we are stacking here? Let me go back to the diagram, the transmission diagram here. Here, We are stacking the symbols. You are putting one after another. You need to wait, and then you put them next to each other and transmit together. And then at the receiver, you wait until you collect all these symbols and convolve them using TD convolution with the channel, and then get to the other domain. Don't you think this causes delay instead of sending a few symbols or even one symbol alone? It does. It does introduce significant delay and complexity. These are the two issues with this. And it's good for Doppler environments where you have environment with objects moving with very large speeds. But for static environments, I don't think you might need this, or it doesn't provide too many advantages actually. In particular, the wireless fading channel response becomes a two-dimensional time invariant convolution response, as we have shown you in the math. All QAM symbols see the same static channel response throughout the transmission interval and extract the maximum diversity of the channel in both the time and the frequency dimension. In certain environment, this significant performance improvement are seen for various MIMO configuration with high Doppler scenario. That's possible also when you have Doppler, you beat OFDM, because OFDM is Doppler is the enemy of OFDM, and this scheme is very user-friendly with OFDM, kind of. Think of it like this. Likes Doppler, this scheme. It benefits this scheme. Doppler gives it gain. In OFDM, the OFDM screw out. It just degrades, doesn't compete anymore when there is Doppler. If you don't have complex receiver to detect Doppler and extract it, eliminate it. The delayed Doppler domain is also suitable for designing RS sequences for multiplexing large number of antenna ports with reduced RS overhead. Since we are representing the signal in the delayed Doppler domain, the RS overhead. RS is reference signal used to estimate the channel. Since the channel representation is compact and there is a sparse behavior in the channel inherently, then the number of parameters you need to estimate is less, and therefore the estimation process is less complex and doesn't consume too much resources. This can result in significant RS overhead improvements for massive MIMO system when you have massive MIMO. 2D only QAM kind of repetition here, QAM symbols and carried in the delayed Doppler domain, of course, we saw this. Wide frequency and observation time exploits full diversity of the channel. That's true because you wait for the whole channel to collect it and you convolve with it. All QAM symbol experience the same channel. Spectral efficiency advantages in high order MIMO, low and medium correlation and high Doppler scenarios, as well as small packets and high code rate, increased density and flexibility in reference signal multiplexing, and many other benefits and advantages. So there are many other research. Now, having understood OTFS as a new modulation scheme, now the concept of it can be applied in general to signal and system area, and also you can integrate it with many other modulation schemes and transmission methods used in wireless communication, like studying the interaction between massive MIMO and OTFS, the interaction between NOMA and OTFS, the robustness of OTFS against hardware impairments, IQ, hardware, phase shift, and the interaction of OTFS with index modulation and number modulation and power modulation and many other areas that when you combine this OTFS with that scheme that was used to serve certain use case, you can bring more advantages, and which is very useful and desirable in wireless communication. So all these are open topics, open research problems to be discussed, and evaluated in the future. And most importantly, to be able to come up with less complex designs at a transmitter and receiver to implement OTFS, because the current designs are extremely complex and also they cause delay. So if you can come up with a design with much simpler designs that can reduce the overhead, that would be a very amazing contribution to the society and community of communication. So with this, we conclude our lecture and we stop here. And thank you very much for your attention, for your patience with me, and see you next time.